Let's start with the synchrotron self-Compton. So in a compact synchrotron source, for instance, imagine a cloud going up in the jet of an AGN. This cloud is the compact source, okay? In such a source, the emitted synchrotron photons can be Compton scattered by the same relativistic electrons that are emitting synchrotron, and this radiation will be boosted, and we call this phenomenon the synchrotron self-Compton. Okay. And the resulting spectral index is approximately equal to the spectral index of the synchrotron source. So, for instance, well, actually the shape is similar. So, if we have here a log parabola, we have something similar there. Okay, this is the SED of a BL-LAC. In AGN jets, these environments are optically thin, which means that the photons can escape very easily. They are almost transparent to photons. They are not transparent, but they are almost transparent. So most synchrotron photons will escape before scattering, and therefore those photons being scattered will be scattered only once, okay, because for them it's very easy to leave the region. However, in some situations, multiple scatterings, also known as Comptonization, can happen. And they can happen, for instance, in the corona of the AGN. Here the corona is represented as this yellow patch here. We are never sure about the real shape of the corona, but sometimes you see it represented like this. So for instance, we have thermal photons leaving the disk, reaching the corona. Here they will be Compton scattered several times, and then they can be emitted to the observer or emitted downwards in the direction of the disk and be reflected to the direction of the observer. To give you an idea, this red curve here is the thermal spectrum from the disk. Okay, this blue power law here is the Comptonized spectrum, which means the spectrum multiple times scattered. Okay, and on the right, this plot here is an example of a plot, an example of the SED of a low luminosity AGN. Do you remember the difference between the accretion disk in low luminosity AGNs and standard AGNs? Do you remember, Marcus? What changes in the disk? Paulo, dai Paulo, vai. Low luminosity AGN. There are AGN and low luminosity AGN. Help us, Anna, please. Save the day. And the other, in the case of low luminosity AGN, the disk is geometrically thick and optically thin. In the case of low luminosity AGN, well, there are several complicated processes there, but we expect the SED to present a synchrotron peak, and it can present multiple Compton peaks. Okay, so this is the first inverse Compton peak of a low luminosity AGN. This is the second one, and this is Bremsstrahlung. Okay, which we will detail in this lesson. And of course, there's a natural limit for this process, which is when the energy of the photon is comparable to the rest energy of the electron. So at this regime, we no longer have the scatterings, and then the process is, how do I say, amortecido, is damped. Okay, let's introduce you to the Compton epsilon parameter. Are you fine? I'm feeling you a bit too quiet today. Okay. Let me introduce you to the Compton Y parameter. In the previous lesson, we saw that the energy gain of a photon is scattered by in the ultra-relativistic limit was something like that. There was a factor of 4 there, but something like that. This you remember, right? We just saw it in the quick review we did. So this is ultra-relativistic case, so the photon is coming from the direction of propagation, okay? If you want to be more precise, you cannot consider this preferential direction, this unique direction. So we consider the cosine theta and cosine theta prime, which is in the rest frame of the electron. Okay, so this is the more general scenario for the scattering of a photon by an electron. So in the non-relativistic limit, which is, let's consider a beta nearly 0, let's take the average of the incoming photons, okay? So the average of the cosine will be 0, average of the cosine in the rest frame of the electron will be 0 as well. However, the crossed term will not be 0. We have it will be minus 1/3. And we can show, and by that I mean you can show this in the problem list, that the net fraction of energy gain is given by this formula here. This is quite easy to arrive. Just take this formula from the previous slide. You have to pass the original energy down here, and you have a factor, the number 1 left on the other side. You pass it to the left side, and you have this the delta energy, okay? The variation in energy. We consider this as the average variation because we are taking the averages of the angles, okay? So you see that the average fraction of energy gain, fraction because we are dividing by the original energy of the photon, will be given by this formula here, 4/3 of beta squared, okay? And now for thermal electrons, we can approximate the average speed of the electrons by the average speed of the thermal particles. Okay, so we have kinetic energy, 1/2 of mv squared equal to the thermal energy, 3/2 of Boltzmann constant times the temperature. So we can isolate the speed, and then we can identify the average beta square. Okay, so beta square is this. Now we substitute in the previous formula, which was this one here, 4/3 of beta square, will become this. Okay, so this is the average energy gain of a photon after being scattered once. Okay, after being Compton scattered once. And the Compton Y parameter will measure the total fractional energy gain of photons while they remain within the scattering region. So the Y parameter is to measure the total amount of energy gain after several scatterings, okay? One or several scatterings. And we use this, I think you are familiar with that, the Thomson optical depth. Are you familiar with that? Like, it depends on the density of electrons. The larger is the density, the higher is the optical depth. It depends on the Thomson cross-section. The larger is the cross-section, the larger is the optical depth. And it depends on the size given by R, by capital R here. So depends on the size of the region full of these electrons that are scattering photons, okay? So we use this concept and the concept of mean-free path. This is more, this you are familiar, no? Mean-free path. Okay. we use this to estimate the number of scatterings that we are having in this region. So for an optically thin medium, this is the first approximation. So tau much smaller than 1, a photon crosses the region only once, and that probability is given by that. So the probability is the density times the cross-section ds. But if you integrate this will be identical to tau. Okay, so at the end, the probability of interaction is exactly tau. Okay, is exactly the optical depth. Do you know what optical depth mean? Do you? Oops, I'm sorry, I forgot to turn this on. Do you remember? So the optical depth is the folding, is the level of folding. If you have, for instance, a light beam going across a cloud, for instance, part of this light beam will cross that cloud and survive on the other side. The amount of light that was lost depends on the optical depth. Okay, so one optical depth is when for instance, in the case of this beam, when 1 over E, the Euler number, 1 over E of these photons were lost. Okay, so this is 1 over E to tau. Okay, so tau equal to 1 is a optical depth equal the standard one. So in radiative transfer, the mean number of interactions along the path is given by that. So this is the mean number of interaction, is the size of the region divided by the mean free path. Makes sense, no? So if you divide the size by the mean free path is this one, is equal to this, which is equal to tau. Okay, so the average number of scatterings in the regime of optically thin medium is identical to the optical depth. Okay, so what this means? This means that most of the photons will not interact. Eventually, one will interact, will be scattered. On the average, this will be the number of scatterings. So number of scatterings will be 0.0000001, for instance. Okay, it's just the average. The photon, or is it scattered or not? But in the average, it will be identical to the optical depth. So, in the other case now, for an optically thick medium, where we have tau much larger than 1, photons undergo what we call a random walk. And after any scatterings, the travel distance will be a function of the square root of the number of scatterings times the mean free path. Do you remember this from Brownian motion? For instance, the rate at which the point-like population of source will spread in Brownian motion depends on the square root of time, or equivalently, the square root of the number of interactions. Okay, let's just rewrite this in terms of n. And so the number of interactions in the case of the Brownian motion, the thick medium, will be r over the size of the region over the mean free path is squared. But we have an expression for that, no? We saw it before. So this is tau. And then n, the number of scatterings, will be proportional to tau squared. Okay. So the epsilon parameter, finally, is the average in fractional increase in energy times the number of scattering, the average number of scattering, which will be tau or tau square, depending on which regime you are. So we just substitute here the value for the energy change here, and then we take the maximum out of the two values. Okay, remember here that we are working only in two extremes. Okay, only for thin mediums or thick mediums. External Compton. Things here become very, very interesting, I think. While the synchronous self-Compton that you see everywhere as SSC involves electrons scattering their own photons. In the external Compton, we have photons coming from outside the jet. Now imagine that you are in a classical AGN, which means a geometrically thin, optically thick disk, and this is emitting a lot of radiation. These photons from the disk, or for instance from the torus, from the dust torus, or from the cosmic microwave background, and something else, or from the broadline region of the AGN, they can enter the jet, and then they will be scattered. However, here the picture is much more subtle, okay? You remember relativistic beaming. You all remember, right? So the jet is being launched from the AGN. So it has a relativistic speed going away from the black hole, okay? These photons in the region will enter the jet, which is moving relativistic, let's say, in that direction. What happens with this distribution of photons? How is this distribution of photons seen by the jet, by particles in the jet? They'll be boosted. Yes, they'll be boosted. However, instead of imagining electrons being shooted from the in the AGN jet, imagine that we have clouds of relativistic electrons going up the jet. Okay, so this cloud, the movement of this cloud is boosted because it's being pushed in the jet. Okay, but the electrons inside that cloud, they are relativistic. So the external photons will be boosted. They enter the jet boosted. Then they will interact with the electrons, which are relativistic inside, and then they will be re-emitted, scattered by Compton scattering. Okay, so this means that, for instance, if the broadline region is shooting optical photons in the jet, these photons will be blue shifted before interacting with the electrons. Do you remember the factor of gamma squared that we had? Now we have capital gamma for the jet, and then the small gamma, it will be something like this. So photons entering in the jet will be already boosted, okay? And those scattered will be boosted by the motion of the cloud in the jet and by the electrons itself, okay? So we have gamma squared. This is we typically call it the Doppler factor, and this is, we call it the Lorentz factor. So it's boosted twice. And you may think, okay, the energy will explode, will be absurdly high, the energy of these photons. But actually they are not. This is kind of tricky, because when these photons enter the jet, they are blue shifted. They have more energy in momentum to break the electrons. Okay, so the cooling, in this case, the cooling of the electrons will be much more efficient. So the electrons are in a case like this, which it's a flat spectrum radio quasar, for instance. It's not a BL-LAC. BL-LAC is the opposite. It's the synchronous self-Compton. In this case of a flat spectrum radio quasar, the temperature of the electrons will be much lower because the incoming photons will arrive with a lot of energy, which will manage to cool the electrons much faster. Ok. Deu para pegar? Okay, so the power emitted via external Compton depends on the energy density. So this formula here is very similar to the synchrotron result we had in the previous class. No, we can rewrite this as this. So instead of writing in terms of the electron classical radius, we write in terms of the Compton cross section. And yes, the energy density that we have to use here is already the boosted energy density. Okay. So in this table, this violet table, we have a very nice summary of the two scenarios, the synchrotron self-Compton and the external Compton. So what are the, this would be better if I could block it to ask you. But what are the seed photons in the synchrotron self-Compton case? Are the synchrotron photons emitted by those the same electrons that Compton scattered them? Okay. In the case of external Compton, they come from the disk, from the broadline region, from the torus, or even from the cosmic microwave background. Okay. Do you all know what's cosmic microwave background? Okay. And where do they appear the most? So the synchrotron self-Compton typically appear in low luminosity blazars, which we call BLX, which is the object of your research. So in your case, we are not seeing this extra gamma square, okay? And it is synchrotron self-Compton, not external Compton. Which external Compton, which we see in the high luminosity blazars, which are the flat spectrum radio quasars that have the Shakura-Sunev accretion disk, geometrically thin, optically thick, and present broad and strong emission lines from what we call the broadline region. The cooling here is slow, and it's quite fast for flat spectrum radio quasars. As I told you, the photons enter already boosted in the jet, then you have high energy photons interacting with the electrons and cooling them. Okay, now I have a challenge for you. Have you ever heard about the Blazer 3C279 and the Markarian 421? Have you ever heard about them? No? Perfect, because this is, you heard about them. So, I don't know. So maybe it's better if Marcella don't participate here. So I want to ask you, which one of these two SEDs belongs to a flat spectrum radio quasar and which belongs to a BLAC? Remember, the flat spectrum radio quasars, the electrons are cooled much faster. They have less energy. Which one is a flat spectrum radio quasar and which one is a BLAC? Oh, we have 50% chance if you don't know. Anna, do you have the answer? Is the what? At higher energies. Exactly. So Markarian 41 is the BLAC. You can see that the energy peak here, well, they are, I forgot to tell you, but they are in the same scale. Maybe you cannot see, for sure you cannot see in this resolution. But they are in the same frequency scale. Markarian 41 has a peak at very, very high energies, while 3C279 has a peak around 100 MeV, more or less, okay? Because these electrons were cooled much more efficiently than in the case of a BLAC. Now, let's deal with this this is a crucial phenomenon that we observe in the absorption, for instance, of gamma rays by the extragalactic background light. Have you heard about the extragalactic background light? No, but you heard about cosmic microwave background. You as well? I haven't heard about the extragalactic. You haven't, but you did. Marcus, have you heard about EBL? Okay, Marcella for sure. So extragalactic background light is the residual light from stars mainly that permeate the universe. Most of it is in the optical and infrared. When a gamma ray, and I say gamma ray because we need very high energies, because we need to have a minimum energy for per production. Opa! Não, senta aqui, vem assistir com a gente. So we need the phenomenon I'm going to describe is the interaction of two photons forming a pair of electron-positron. Okay, for this interaction to happen, the summed energy of these photons has to be at minimum a bit higher than the energy of the two electrons. I say a bit higher because otherwise they don't conserve momentum. Okay, so if you have exactly the energy for creating two electrons, it will not happen. Okay, so imagine I have a gamma ray, it's traveling through the universe, it finds an infrared photon in its path, it can interact, the probability is low, but it can happen. It can interact and form a pair of electron-positron. What happens with the original gamma ray? It's lost. I cannot observe it. Okay. There is a kind of reprocessing called gamma ray halos, but this is another thing. So this process of gamma annihilation we observe in the spectra of lasers, especially with Cherenkov telescopes, which are these gamma ray telescopes based on the ground. Okay, for the Fermi lat, for instance, you can observe in some cases, but Fermi is not actually optimal above 100 gigaelectronvolts. So you can see traces of it, but it's much harder to do this with Fermi than with MAGIC, for instance, or LST. Okay. Okay. So this is the condition. The energy of the gamma ray multiplied by the energy of the target photon, which is typically, in the case of EBL, infrared photon. It has to be larger than the square of the rest mass of the electrons. Okay, and there are these factors here that depend on the incoming angle of this interaction and also on the conservation of momentum. Okay, so and the final effect is a suppression of the gamma ray flux above a certain gamma ray energy. This is very interesting because for those of you doing cosmology, gamma rays of very high energy, they are not very useful for cosmology because they simply are absorbed by the universe. Can you imagine about? Just think about it, because I'm saying basically that the universe is opaque to very high energy gamma rays. Okay, it's just they cannot propagate. Well, they cannot propagate through cosmological scales. Huh? They need a lot of space before interacting because the probability is low. But this puts a limit in gamma ray astronomy that we call the gamma ray horizon. So after a certain energy for a certain redshift, we don't see gamma rays anymore. Okay, it's called the cosmic gamma ray horizon. Okay, this one, unfortunately, I cannot derive this with you. It will be very, very stressful to derivate this, and probably is not very useful. But it's important that you know that this thing exists. This is the gamma interaction cross-section, okay? Average in polarization. So it depends on the Thomson cross-section and on this S parameter. S is given by this, and epsilon is given by this, okay? Epsilon is the non-adimensional energy of the photons, okay? So if you want to compute the optical depth for this cross section, you can simply integrate the density of target photons over the multiplied by the cross section. Okay, here I'm putting a bar over the sigma because I'm averaging again on the angles. Okay. And what you have is something like this. This one I computed, so please ignore the unit. There are no units in the y-axis, but this is tau. But these values here, they are arbitrary, okay? So this is what we expect. The shape is okay, okay? This is the shape of the optical depth for a photon leaving the jet of an AGN and interacting with photons in the broadline region. Okay, so you see, for instance, this peak here, the main peak, is centered more or less in 52 gigaelectron volts, which is gives us the maximum probability of interaction of Lyman alpha photon with the gamma ray photons. Okay. So this every time you see a bump here means that there is an emission line in the broadline region. Okay, so every emission line will increase the optical depth by a little bit. And okay, and Bremsstrahlung, which is the German word for break-in radiation. It's considered, we consider it thermal radiation. We call it thermal. However, the spectrum is very different from the black body. And the radiation is emitted when a particle is decelerated. It loses energy. When it interacts, for instance, when an electron interacts with a proton or an ion. Okay, so it will change direction, change speed, and then it will emit a photon. Have you ever heard about Bremsstrahlung? Heard. Have you ever seen a figure like this? Yes, I don't like this figure because I think it's too superficial. Okay, so that's why I did this simulation to show you really what's happening, and that's why we did that quick review in the beginning of the lesson, where I showed you the particle moving and the electric field emitting the electromagnetic wave. Okay, this will be very, very useful for us for the case of the Bremsstrahlung radiation. Okay, so the Larmor formula in CGS units, as we saw in the previous classes, is this one. This is the acceleration. Okay, the electron charge, speed of light. So this is the power. The total energy is we just need to integrate the power in the time. So the integral becomes this. And now we can convert this total power, which is as a function of time. We can use the Parseval theorem to transform it to the range of frequencies. Okay. So this is for a generic function. And this f tilde is simply the Fourier transform of the function. So now we can apply that to our case. And we have that total power in terms of the frequency is simply this expression here. So if we compare this is total power in terms of frequency. If we compare this with this integral here, W is equal to the integral of the power over frequency, derivative of frequency, times the frequency. Can you see this? Can you see that we can write omega as this? Okay, so by comparison, this with this derivative here, we have this. Okay, so in order to get the spectrum, which is the power evaluated in each frequency, we just need to know the Fourier transform of the speed, of the acceleration. Okay. Now, okay, let's see the Coulomb encounter geometry. Let's assume a straight line passage of the electron close to an ion. So the r coordinates will be simply vt, this will be the x coordinate, and b is the impact parameter, is the y distance. Okay, this is the norm of this vector. So the Coulomb acceleration is given by this, which we can rewrite, putting this here, and separating into components. This is a vector, so we can separate in the two components. We have the x component of the acceleration that can be written like this, while the y component of the acceleration can be written like this in terms of the impact parameter. Okay, do you know what's impact parameter? Impact parameter is simply the, imagine you have a photon, imagine you have a proton here, and the electron is here, will come here and do like this, okay, when it interacts. What we call impact parameter is this minimum distance here in the maximum approximation, okay? This is the impact parameter. Okay, so now we have the two components of acceleration in the x direction and acceleration in the y direction. This is in normal space. We need to Fourier transform this, okay? So let's do that. So these are the results we just got in the previous slide. Let's Fourier transform each one of these components. Let's do this first for the x component. We have all of this. The results are given in terms of modified Bessel functions of the second kind. And yes, now we can put them together. And assuming that Xi can be written in terms of the frequency and the impact parameter. So just put these two results together. So the Fourier transform of the acceleration is given by that. This is the exact spectrum for a collision. Okay, is it too cold, Anna? If you want to, because okay. So this is the exact Bremsstrahlung spectrum. However, this, for me, it becomes much more interesting when we consider the extreme cases. So let's consider the regime of very low frequencies. Remember, frequency is here. So low frequency means low Xi. Okay, let's consider for a moment the very low frequency and the very high frequency regimes. We define the collision duration. This is just the result from the previous slide. In the low frequency regime, we have that the modified Bessel function is given by this natural logarithm, while the other is given by 1 over Xi. Okay. So let it finish, then I'll describe everything for you more slowly. Okay. The result at high frequencies. Okay, the formula that we found for the spectrum in the previous slide depends on C square and the modified Bessel functions of the second kind. Okay. In the low frequency regime, we can approximate K0 as minus the natural logarithm of Xi over E, and K1 as 1 over Xi. Okay. What happens if we substitute this here and have to multiply by this extra Xi squared? When Xi is much smaller than 1, what happens with this first term? Vanishes, goes to 0. What happens to this? This is squared, so this is this here is squared. It will go to 1, right? So this for me is very impressive because at low frequencies, the Bremsstrahlung spectrum is a constant. It's very rare to find this in anywhere in astrophysics. No, it's very, I don't know. You always expect something different from a constant, no, for an spectrum. But for low frequencies, the Bremsstrahlung spectrum is a constant. Okay, it depends on the temperature, but for a fixed temperature, it will be a constant. While in the high frequency regime, both cases can be written like this. If you substitute here and take the square, the expression will become proportional to pi Xi exponential of minus 2 Xi. Even if you have this pi Xi here, the exponential will, at the high energy frequency, would completely dominate. Okay, so in high frequencies, we'll have a spectrum that will disappear. Okay, it will decay exponentially. Can you see it? So to visualize this better, let's see the spectrum. Okay, so in low energies, it's a constant, and then at high energy, high frequency, it drops dramatically with an exponential. Okay. And to give you a more physical meaning, I'm giving here some typical values for this parameter. So the impact factor is of the order of 1 angstrom, and V, which is the speed of the electrons, the thermal speed of the electrons, ranges more or less from 1% to 30% of the speed of light. And the Vmax, it can go from radio to up to X-rays. Okay, so the range is very broad. Everything clear? Entendeu o que é que eu desenho? Agora eu vou desenhar. So now you have in mind the image from the review, where we have an accelerated particle changing the local magnetic field, and this propagation, in the electric field, will propagate as photons. You have that in mind, no? So if you have two charged particles, things are quite a bit more complicated. They'll be like that. Electron approximates to a proton and emits these waves, and right here, where they superpose, they accumulate, is the emitted photon. Okay, let me try to do this with you very slowly. Oops. Okay, let's go step by step here. This red in the middle can be a proton, can be an ion. Okay, this thing in the left upper corner is the electron. Okay, these blue lines are the electric field lines connecting both. Okay, so the electron is, the electron is approximating the proton, and nothing happens until it accelerates significantly. No? Okay, let me see if I can catch a perfect moment here. You have to play it by yourselves at home, I think. But you can see, okay, I'll draw it here. You see something like that. Here is the proton. Here is the electron is here. Here is where the field lines think. Okay. Yes. This is the proton. This is the position that the electron was supposed to be, but it's so fast that it's not there anymore. So it's, for instance, it's here. Okay. So what we have is this. Can you see? It's the same thing as in the other animation. And for instance, this line is coming here. It was going to connect to the electron, but the electron is already advanced. So it will be like this. And this line here will be something like this. Okay. And then you do this all sorts of breaks in the electric field lines, and then this circle of break, if you take it and propagate, because these breaks in the field lines will propagate, you have these disks here. These circles. So when the field lines start to break due to the now I got it. So the electric field line from the proton here, it was going directly to where the electron was. Okay, but the electron already advanced. So you see these breaks in the electric field lines, and as the electron propagates, these perturbations will just grow. Okay, at the speed of light. And if you do that several times, here I'm doing it discretely, but of course you have a continuum. Okay, so if they propagate in the position where they are superposed, it will be where the photon is emitted. Okay. Clear how Bremsstrahlung radiation works? What's the shape of the Bremsstrahlung spectrum at low frequencies? It's a constant, and at very high frequencies. Exponential decay, exponential cutoff, exactly. And for today, this is the list of problems. So show that the average energy gain after one inverse Compton scatter is this. May remember the asterisk I put there in the slide. And this will be very interesting. What is the gamma ray energy that maximizes the cross section for per production, the gamma-gamma interaction, for a green photon with this frequency here, 6 times 10 to 14. What I mean is that this formula here, for a photon, for a green photon, this function here, the green photon will enter here, epsilon t. Okay, I want you to find the value of epsilon that maximizes this area, this cross section here. Okay, you see that, well, if you play with it, you see that there is a optimal energy for the gamma ray for this interaction to happen. Okay, and that's it for today.